you ready to share your screen?
Oh, actually, I'm not. Just give me a second. I got distracted by
all that was being discussed.
Yeah, actually.
Hard to believe that, isn't it? That Daniel would get distracted thinking about math.
Oh, yeah, I think I'm ready though now.
Okay, so our next speaker is Daniel Chin, who is going to be talking about mutually unbiased bases and Hadamard matrices.
Okay, can we see my screen? Thanks, Dr. I, for the intro. Cool.
Yes.
Wow, it's so great to see so many people here, and so many faculty members, so many cool people that I really love a lot. Thanks for being here, y'all. Yeah, as Dr. I said, I'm here to talk to you guys about mutually unbiased bases and Hadamard matrices. So this is my senior thesis work. It's largely based off of the work of two mathematicians. Well, one of them is a physicist. First being Thomas Dirt from the Central School of Marseille, and the second being Ingemar Bankston, who is a physicist, a theoretical physicist at Stockholm University. So as an overview, I'll first begin by talking about mutually unbiased bases. I'll give you the pairwise definition, and I'll give some examples in R2, and I'll ask a packing question that'll kind of motivate the next two theorems, the first being a bounded theorem, and the second being a maximality theorem. And I'll mention the open problem that I'm working on, or that I've been kind of tackling throughout my process. Then I'll move into these tools called Hadamard matrices that I use to tackle this kind of question and try to understand this thing. And I'll give you a nice important example of those Hadamard matrices that we need to use. I'll give you an equivalent statement between mutually unbiased bases and this new object called mutually unbiased Hadamard matrices. And afterwards, I'll wrap up by giving a standard construction for mutually unbiased Hadamard matrices over prime dimensional vector spaces. And so I'll give you an example of that construction in 3, recover some mutually unbiased bases from that construction, and then try the standard construction over composite dimension and tell you why it fails. So let's talk mutually unbiased bases. As I mentioned, it's a pairwise definition between orthonormal bases. And so you have a basis E and a basis F. You take an arbitrary basis vector from E, take an arbitrary basis vector from F. If you hit them together using the inner product and square their norm, and then you always get 1 over D regardless of which bases vectors you pick, then we call these two bases mutually unbiased. And as I mentioned, I give you an example in R2, and an easy example to visualize is if we take the standard basis vector, you take a copy of that, you rotate it 45 degrees, then these two bases will be mutually unbiased. Similarly, if we flip the purple basis across y equals negative x, we could also flip it across y, the x-axis itself. These bases would still preserve the mutually unbiased property that we care about. So you can kind of get a sense that mutually unbiasedness doesn't really care about the positive or negative direction of the basis vectors. Additionally, we might also note that if we rotate our bases by an arbitrary angle r, in this case in the second figure we have it by pi over 12, that this also the mutually unbiased property is still preserved. And so there's some angle preservation going on there. But this is a simple example from R2, and there are much larger vector spaces like R3, R4. There's even complex vector spaces that exist out there. So a question you might ask yourselves is, how many orthonormal bases such that can we squeeze into arbitrary size vector spaces such that the mutually unbiased pairwise property still holds? And as I mentioned earlier, it depends on the dimension. And so we have this bounded theorem that depends on dimension D. And we know that the maximum number of mutually unbiased bases will be bounded below by the smallest prime power divisor, p to the n plus 1, and bounded above by the dimension of the vector space, D plus 1. I will mention this real quick. So for example, if we were in D equals to 6, so C6, then we would be bounded below by 2 plus 1, and we would be bounded above by 6 plus 1. So between 3 and 7, we'd have that many mutually unbiased bases that we can find. What we might notice though is that from this bounded theorem, if we have D equal to a prime power itself, then we would say that the bounds are saturated because the lower bound would be the same as the upper bound, right? We would have P to the K plus 1 on the bottom and P to the K plus 1 on the top. So that would imply that the maximum number of mutually unbiased spaces we can get and actually achieve is P to the K. And this is a nice characterization of mutually unbiased spaces, a very solid, robust characterization of mutually unbiased spaces in prime power dimensions, but we don't really exactly know about what that means for non-prime power dimension. So the open problem I've been kind of thinking about is whether or not there exists a maximal set of mutually unbiased spaces in arbitrary dimension. To give you a little history on mutually unbiased spaces, these objects were not really formally defined until around 1960, and they're first introduced in the literature that I've read by Julian Schwinger in 61 years ago. So again, the objects we're working on are these things called, are these sets of orthonormal bases. The property that we care about is an angle preserving property, and this question type is a question about the existence of a maximal set of mutually unbiased bases. For our talk today, we'll be restricting our work to over the complex numbers, but you can easily think about mutually unbiased bases over the reals and other arbitrary fields. So let's talk about Hadamard matrices. As I mentioned, they're an important tool that we use to examine these theorems, and they're one of many tools that we use to examine these theorems. So what is a Hadamard matrix? Well, definitionally, a complex Hadamard matrix is a square matrix with unimodular complex entries, and the adjoint product itself is going to be a scaled identity. So there's two main properties that you call in the definition. The first is that we have this notion of unimodularity. It's just a really big word that means that the length of all these entries in this matrix are going to be 1. And second property is that H times H star, or H adjoint, and if you haven't seen the adjoint before, it's pretty much an inverse that respects the inner product, and the inner product is what we used to define the mutually unbiased property earlier. And so we have that H times H adjoint is going to be equal to D times I. So a nice example, a really important example of Hadamard matrices that we want to talk about, especially today, is the Fourier matrix. So the Dth Fourier matrix has complex entries of omega D to the power of j times k, where j is the row number and k is the column number. And so you might ask yourself, what is omega d? And I'm going to kind of glance over this really quickly. This omega d is the first Dth unity, where omega d is explicitly given as e to the I 2 pi over d. And if you haven't experienced any sort of notion of roots of unity before, what's important to know is that roots of unity, the Dth root of unity, the set of Dth unities partition in a nice set into D equal size things. And so we want to exploit this this nice rotational symmetry that roots of unity have. So let's talk about some examples. So as we flip through some examples of the first four Fourier matrices, we might notice that things get really cluttered very easily with all these omegas flying around. And we might notice that for every f sub d, it actually depends strictly on omega d, like we had noticed earlier. So we can look at this isomorphic object that is a lot more clear and a lot more easier to look at. And this isomorphic object that I'm talking about is the matrix of exponents. The matrix of exponents has this nice name from the literature. It's called the log Hadamard matrices or log Fourier matrices, but you also might hear me refer to them in this talk today as the adjacent matrices, because that's how I first talked about them when I first ran into them. So looking back at those examples now, we might notice that there's quite a bit of nice symmetry in these matrices. If you look at the first row and first column, you might notice that there's always zeros and they're just all composed of zeros. We also might notice that on the left side of the equality, that along the diagonals, we have just a bunch of squares. So we have 0 squared, 1 squared, 2 squared, and 3 squared, and so on and so forth. Additionally, we might know that across the diagonal, we are symmetric across the diagonal too. And so this might make a lot of sense if you think about the fact that j times k equals to k times j, right? That's pretty much where the symmetry is occurring from. And that makes a lot of sense because integers commute under multiplication. So I think now I'd like to give you, it might be not so clear as to how these Hadamard matrices relate back to mutually unbiased bases, but there's actually a very nice equivalence statement between mutually unbiased bases and these mutually unbiased Hadamard matrices. In fact, we know that if there exists a pair of d by d mutually unbiased Hadamard matrices, then there always exists a pair of mutually unbiased bases. If you're interested in hearing the proof of the theorem, we can talk later about that too, but I won't give it here right now. You might ask yourself also, because I haven't defined what are mutually unbiased bases, or sorry, mutually unbiased Hadamard matrices. And so I'll give you the definition. We say that two Hadamard matrices H1, H2 are mutually unbiased if the adjoint product of the two is going to be a Hadamard matrix that's just scaled up by the square root of the dimension. And so how does this relate back to the mutually unbiased bases? How can we begin to develop some intuition for where are the objects that we cared about before, in particular the orthonormal bases? In the case of Hadamard matrices, these orthonormal bases are actually encoded in the sets of column vectors of H1 and H2. And so we can then take the theorem we had from earlier about maximality of mutually unbiased bases and extend that to a maximality theorem of mutually unbiased Hadamard matrices. And so awesome, now we have this nice theorem about mutually unbiased bases and mutually unbiased Hadamard matrices, and we've defined this nice equivalence relation too. So let's talk about the standard construction over some arbitrary prime dimension P. In order to begin doing that, I have to first tell you about this last object that I'm going to introduce. It's called this inphasing matrix. And so we say that the dth inphasing matrix, E sub d, is a diagonal matrix with entries given by the delta Dirac function times omega d to the j times k, where j and k iterate over 0 to d minus 1, and j is the row number, k is the column number. And if you kind of are getting the theme a little bit, we look at some examples of E3 and E4, we might notice that, wait a second, we've seen these objects before kind of in terms of the Fourier matrices. These are really just the diagonal elements, and that makes lots of sense to us because the delta Dirac function is 1 every time j equals to k, and 0 when j doesn't equal to k. So we already have some familiarity with the inphasing matrix in terms of the Fourier matrix. So cool, now I can tell you what the actual standard construction is. So here's the set, MUHM, I've defined it as such, and every element of MUHM from r equals to 0 to d minus 1 is given as r copies of E sub d, the inphasing matrix. You hit them all together and you hit it against F sub d. And I claim that this is a sufficient set of mutually unbiased Hadamard matrices that suffice the definition of mutually unbiased that we defined earlier. And so here it is again. In order to prove this, we might want to take, we'll just want to have take two arbitrary elements from our set of mutually unbiased Hadamard matrices and show that this definition holds. So we might observe that if we do take two copies, right, that with some nice adjoint properties, we can rearrange our matrices so that this FD adjoint times E to the E sub D j minus 1 times F sub D. But wait a second, by the definition of our mutually unbiased Hadamard matrices, this is precisely just H0 adjoint times h to the power of j minus 1 or j minus I. So the problem then reduces, right? The problem of proving this theorem then just simply reduces down to showing that really an arbitrary, the 0th Hadamard matrix is going to be mutually unbiased to any arbitrary Hadamard matrix, rth Hadamard matrix in that set. And so it's efficient to talk about this lemma here. If we can, and this lemma just pretty much is just a restating of the observation and saying that, hey, if we can show this product matrix P equals to the square root of D times any Hadamard matrix, then we're all set. That theorem is going to be pretty much proved. And so from there, the proof idea becomes kind of simple. We want to we just want to show that this product matrix holds all the Hadamard matrix properties that we talked about, those two that we were talking about earlier. The first being showing that all the entries of P has a modulus of D, because we're scaling up all of our unimodular entries by square root of D. To do this, actually, this surprisingly was actually probably one of the more trickier parts of my thesis, and it had to do a little bit. I had to use some algebraic number theory and some cute delta Dirac notation manipulations as well. And if you're interested in doing that, I can be glad to talk about that as well. The second part was actually a little bit easier to do, and that was showing that P adjoint, the adjoint product, is going to be equal to D squared times the identity. To do this, I just used some nice adjoint properties, so properties of the definition of the adjoint too. And so yeah, so this is the way that I went about proving this theorem. So let me give you an example, a very simple example to leave you with. And so I'll give you an example in t equals to 3. So here's the set of Hadamard matrices that are mutually unbiased. I just kind of constructed them and wrote them into the log form, just so it's easier for us to read. As I mentioned, we can take those column vectors, and if we exponentiate those column vectors, if you exponentiate omega to the d, omega sub 3 to those column vectors, and scale them all down by 1 over the square root of the dimension, which in that case is 1 over the square root of 3, we'll recover a set of mutually unbiased bases. But wait, Daniel, you told us that a maximal set of mutually unbiased bases is going to be equal to the dimension plus 1. In this case, we're in dimension 3, so where's the fourth one? And that would be a really good observation. And the fourth one is going to be actually the standard basis. So I claim that the standard basis 1, 0, 0, 0, 1, 0, and 0, 0, 1 is actually going to be mutually unbiased, pairwise mutually unbiased to all these other already pairwise mutually unbiased bases. And so yeah, there we go. We've recovered, we've done an example of recovering a full set of mutually unbiased bases in prime dimension. So now let's wrap up by talking about standard construction over 6 and talk about where it fails. So I'll order my mutually unbiased base or Hadamard matrices like so. The first 3 are going to be on the top row. The latter 3 are going to be in the bottom row. And so here's the first 3. Here's the second 3, and done these computations. And if we look at each of these stacks, if we look at the first stack here, we might look at the fourth column vector and notice that, hey, wait a second, that actually kind of just shows up as our first column vector here. If we look at our third column vector here, we might notice that 0, 2, 4, 0, 2, 4 shows up as our sixth column vector. And I claim that if you look at any of these 6 vectors here, you'll find its copy, the same exact copy, somewhere along these 6 column vectors here. And so what you'll notice is that if I say this is the 0th Hadamard matrix, then the third Hadamard matrix is going to just be a permutation, a permutations of the columns of the first of the 0th Hadamard matrix. Similarly, the second Hadamard matrix, the first Hadamard matrix here, will be a permutation of the columns of the fourth 0, 1, 2, 3, fourth Hadamard matrix. And again, the second Hadamard matrix here is going to be column permutations of the fifth Hadamard matrix. So no dice, that doesn't work. We don't get a full set of mutually unbiased Hadamard matrices, so we won't get a full set of mutually unbiased bases using this approach. But thankfully, there are a lot of other directions we can take. There are a lot of other algebraic methods that I didn't bring up. I studied in particular another algebraic method with unitary operators, and if you want to talk about that, I can tell you that also later on. I just didn't have enough time to tell you about it today. There's also another method with while operators. That was a bit out of my comfort zone, so I didn't talk about that one too much, but I can give you some research to look at that. There also exist geometric methods that I looked at some points. If some of you might have come to my, actually for the geometric methods, I was intending to write this as mutually unbiased basis, the MUB polytope, and I don't think I mentioned that in my fall talk. But I did mention in my fall talk some combinatorial methods with finite affine planes and finite projective planes. So if you've taken a combinatorics class before, you might have run into those as well. And there's this really nice relationship, explicit relationship that between mutually unbiased bases and finite projective planes, finite affine planes, and also mutually unbiased or mutually orthogonal Latin squares. We can also look at mutually unbiased bases in physical systems, and they show up a whole ton in quantum mechanics. And yeah, the only other direction I have besides those 4 is just to have fun. So yeah, here are my references, or primary references. If you're looking for more references of these, feel free to reach out to me. I have plenty of references for you to look at. And yeah, I just want to take some time to thank everybody who came to this talk. I want to thank my friends and family, especially my friends who are not from Kalamazoo. Friends from Kalamazoo, thank you so much for being here. Friends from not Kalamazoo, thank you for taking the time and dealing with this tricky situation for getting to here. Thanks for my family, my dad and my mom for being here and supporting me in my math career and everything else. Thanks for the faculty, physics faculty, math faculty, human philosophy faculty, other faculty members. Kristen, thank you so much for all your support. A special thanks to Dr. Endermont, my SIF advisor, and also Dr. Chawasawa. You guys don't probably know him, he's not here, probably. He was my J-term advisor in Budapest and inspired a lot of the topic. And thanks to the audience for just being here and listening. So yeah, that's the end of my talk.
Okay, thank you. I saw lots of hands there, and I will add mine to them. And we've got a few minutes for questions if anyone would like to ask a question. Somebody's hand is up. I can't see whose hand. Saida?
Yes, hi. I guess I'm not really like a maths person, but I'm here to support DQ. I guess a question I would have for this research, like as I'm trying to understand it, why does this topic really matter? Like, why do we care about this subject? If that's an okay question to ask.
That's a great question. Thank you for asking that question. Actually, I've prepared some slides for that. So why do you care? Yeah, so for my physics friends in the background, and for my quantum computing friends in the background, this has a lot of applications to quantum mechanics. I've been alluding that to so much. And my quantum information theory friends who are in the background, this matters a lot to us. And you might have heard Mihai talk about this a lot. And so I'd like to talk about what quantum probability measurement is. And so in quantum systems, we talk about events as vector spaces over some arbitrary Hilbert space. You don't have to know what Hilbert space means, just treat it like a vector space. And if you don't know what a vector space is, it just means space pretty much, because most spaces that we care about behave like this. And so we may also state that for an input event, the probability of measuring an input event as some output event is going to be noted as this inner product squared, the norm of the inner product squared, as which is really similar. This is exactly the way we kind of defined, or this operation is what we defined our mutually unbiased basis property as. And so if we want to measure arbitrary events from mutually unbiased bases, they will always have the same probability, right? It will have the same exact probability 1 over d. And so that's why we call it unbiased, because they don't really care about each other. And so another example, right, a really important example for especially our quantum mechanics set here is this set here. And if any of you guys recognize this set, you might recognize it as the eigenvectors of the Pauli matrices. And so what we might point out is that the mutually unbiased bases describe the spin-half system. And so yeah, these guys are pretty important in terms of quantum mechanics and in terms of quantum information theory, in terms of, you know, quantum computing, quantum error correcting codes as well. So thanks for the question.
That sounds like a plant. Are there other questions?
It was.
I'll ask then quickly. What is the piece of this that you are most excited to look at next? Notice not in general, but like next, what's the piece you're most excited to think about?
Oh, there's a lot I'm excited about. Are you talking about in terms of like
choose
which of the directions?
In this,
oh
exactly,
man,
this,
that is really difficult to think about. I think that what's really interesting is that I've seen a lot of similarities between the recent work that I've been doing with Dr. Gandini and the work that I've been doing with this project, and especially in terms of invariance as well. And so we've been dealing a lot with kind of, yeah, we've been just dealing with a lot of similar operations, similar relationships. We've been dealing with these characteristic functions, which play nicely with the roots of unity, which are a huge important topic in determining where mutually unbiased bases are, or at least constructing them for our standard construction. So I'm excited to try to tie together my thesis work with the research work that I'm doing with Dr. Gandini too.
Francesca?
I don't know if this is a connection, but something that came to mind as I was looking at your matrices. What do you know about their determinants? Because they kind of look a little bit like a Vandermonde. Like, they're not exactly a Vandermonde determinant, but something like it. So I was wondering if there is some like spatial properties of their determinants.
That is a really good question. I did not look at their determinants. That is a really good question. I'll look at them and I'll get back to you. I'll actually get back to you. That's a great direction to go into.
Any other questions?
I have a quick question, and imagine yourself as a first-year student entering K, and you just watched the talk that you gave. Do you think that you would have thought yourself capable? And what would you say to those out there wondering what they're capable of in mathematics?
Oh, wait, could you repeat the question? Sorry.
No, yes. What I'm saying is, you just gave a very high level talk, and my question is how well you think you would have understood this when you entered K? And to students out there that may be wondering, could I do this? What would you say to them?
Oh yeah, absolutely, 100%. I came into K I didn't come into K wanting to do math. I will for sure say that. I came into K wanting to do philosophy. And I actually didn't have a really good experience in math in my high school and especially early high school. And I don't know, the faculty here have been really great to me. And especially, I've just met a lot of great community members here, and I've just been really blessed, I guess. So for students who are first years here, second years here, and seeing this talk and seeing all the cool things that I'm doing, I'm really excited to talk to you guys about them. And I'm also wanting you guys to know that it's very doable to get to. I'm not really sure if I'm answering your question correctly, but I just think that the department here is they've supported me so much, and I'm really grateful for that. And I've been blessed to have a really awesome community that's pushed me to be able to give such a high level talk, I guess, Ben.
Thanks. We really appreciate those nice words. And let's thank Daniel once again. We have 2 or 3 minutes before I believe Isaac takes over. So stretch your legs, and yeah, in another 3 minutes we'll begin.